you should be able to see the slides. Please let me know if anything is not okay for you.
Okay.
Okay, so after having examined the Sonnenfeld problem in our last lecture, today we will consider again the same configuration and also other more complex planar configurations. Our aim will be that of discussing two important wave species. First of all, we will say something about lateral waves, and second, we will introduce the concept of leaky waves. Okay, let us start with lateral waves then. And to introduce the concept, let us consider the very familiar problem of plane wave incidence upon a planar interface between two different media that may be assumed to be simple media, in particular isotropic dielectrics. As we all know, in this problem there arise two more waves, one reflected plane wave and another refracted plane wave, of course, in addition to the incident wave. Now, it's interesting to see that if the field impinges from the medium where the speed of the wave is lower, that is the optically denser medium, then the refracted wave emerges at an angle which is larger than the incident wave with respect to the normal direction to the interface. And we know that there is a critical angle, after which we have total reflection, that is, the transmitted plane wave is not uniform anymore, but it is rather evanescent in the direction orthogonal to the boundary between the two media. This evanescent wave is described in terms of a complex transmission angle, theta t, with a real part equal to pi/2 and some imaginary part, theta tj. Okay, this is all very well known. Let us try to imagine what happens in a ray optical description of the wave field, in which you interpret everything in terms of wavefronts, rays, and ray tubes inside which the power flows. Now, this picture of the wave process finds a fundamental difficulty exactly at the critical angle. In fact, as you can see in the top figure, if our incident angle is smaller than the critical angle, then the power associated with the incident wave splits into a part which is refracted in the upper medium and another part which is reflected in the lower medium. If the incident angle instead is larger than the critical angle, then all the real power associated with the incident wave gets refracted. That's why we call this phenomenon total reflection, because the reflection coefficient has a magnitude equal to 1. However, exactly at the critical angle, the direction of propagation of the transmitted wave should be grazing, that is exactly at pi/2 angle with respect to the normal, to the interface. So the power flux, the tube that contains the power flux, shrinks into a zero cross-section tube, so we could not tell where the incident power goes in this ray optical picture. However, it is plausible, at least intuitively, that the ray that is critically reflected may also, by reciprocity, be refracted back, so react back in the denser medium, and therefore this could be a mechanism for the power to be reflected in the lower medium. So we would have an evanescent wave in the upper medium that propagates grazing at the interface, so along the interface, and during its propagation there would be some power that comes back in the lower medium, and that's what we call the lateral wave. So we have a domain of existence of the lateral wave, which is bounded on the left by this dashed line, okay, that depends, of course, on the location of your source. This is the intuition behind the concept of lateral wave, and this is what we will now investigate more in detail starting with the mathematical formulation of the Sommerfeld problem that we have already addressed in the previous lecture. In fact, as you may recall, in the previous lecture, we have already introduced the concept of the lateral wave as the contribution to the potential excited by a vertical dipole given by the integral around the steepest descent path, which is this vertical folded green path here in the picture, that goes through the branch point K2, which is the branch point of the denser medium in the example we saw in the previous lesson. That is because in the previous lesson we had the source in the lighter medium, for example in a vacuum or in air, and in that case we did not have the phenomenon of critical angle and total reflection. And in addition, if the dielectric is enough lossy, like for example for the ground, then this K2 wave number is a complex number with a non-negligible imaginary part, as in this figure, and therefore its contribution to the total potential is exponentially smaller than the contribution that comes from, for example, the other steepest descent path, the one represented here in gray. So in that situation, so again, the source in the lossless medium and therefore the dielectric without sources and lossy, then in this case, the lateral wave contribution is negligible. However, if you exchange the role of the two media, so now you have your source inside the denser medium, and if the dielectric is low loss or even lossless, then it is possible that the lateral wave becomes non-negligible. And this is what we'll now study in detail, considering this vertical dipole source again at vertical abscissa Z prime, placed now inside the dielectric having relative permittivity epsilon r. This is the lower medium, whereas in the upper half space we have vacuum. We are again in a time harmonic regime with radiant frequency omega, and as usual, we associate to the vertical electric dipole an amplitude, which is this complex coefficient P0. Okay. Now, the mathematics is exactly the same as in the previous lesson, so we saw that it is possible to represent the magnetic potential excited by this source, which is vertically directed because the field is purely Tm, in terms of this representation, in which you can see in the lower medium we have the incident wave, which is the usual free space Green's function for medium number 2, and this is known in a closed form. And then there is the reflected wave, in which you can see here is the voltage reflection coefficient gamma T for Tm waves. Then there is this ratio, which is the one-dimensional Green's function for Helmholtz equation in the z direction. Then there is the Bessel function of order 0 and argument k rho, and we integrate with respect to the radial wave number k rho with integration limits from 0 to plus infinity. So this is an example of a Sommerfeld integral, which is nothing but an inverse Hankel transform of order 0. Similar structure has the transmitted or refracted field, in which now you have 1 minus gamma inside brackets, and again the free space Green's function for the one-dimensional equation, and the Bessel function J0. Now, this reflection coefficient is, in this case, is the reflection coefficient for incidence from the dielectric, because now the source is inside the dielectric. Okay, so it has a different sign with respect to the reflection coefficient that we used in the previous lesson. However, the structure of the singularities is of course the same. So what we have is that we have two pairs of branch points, one originating from the wave number in the upper medium, K1, which is now smaller than the wave number K2 in the lower medium. And we are able to extend the integration limits from -infinity to +infinity, thus integrating along this orange path, which is the extended Sommerfeld integration path. We observed last time that our integrand has a single pair of poles, the Sommerfeld poles, that in the case of a lossy ground give rise to the Zennec wave. However, here we are assuming that the media are both lossless. So this pole is located exactly on the real axis. As you can see, here we have Kp on the positive real axis and its negative counterpart, -Kp on the negative real axis. This pole, however, is on the lower rim of the branch cut that you can see here in dark red, associated with K1. So it does not contribute to the representation of the field. It's an improper surface wave because it's located in the lower, in the Riemann sheet number 2. And so we don't need to care about the contribution of this pole singularity. So what we can do is the usual saddle point evaluation of those integrals. The saddle point, as we saw in the last lecture, is associated with the angle theta that is defined by the observation point. And this angle defines the position of the saddle point, KSP, which is located on the real axis between 0 and K2, because its value is equal to K2 times sine theta. If the observation angle theta is smaller than the critical angle theta c, by definition, the critical angle is such that K2 times the sine of the critical angle is equal to the wave number K1 in the upper medium. So this means that the saddle point, KSP, is located on the left of the point K1, of the branch point K1. Okay. Of course, the critical angle has the usual expression, the inverse sign of the reciprocal of the relative permittivity of the denser medium. Okay. So in this case, nothing special occurs. You can deform the extended Sommerfeld integration path from its original location to the gray steepest descent path that goes through the saddle point, and you can perform your asymptotic evaluation as usual. What changes is when instead the observation angle is larger than the critical angle theta c. This means that now the saddle point is located between K1 and K2. And in this situation, what you need to do is to introduce an additional contour, this SDP1, that runs vertically. It is a folded contour that passes through the K1 branch point, in addition to the steepest descent path in gray that was present also in the previous slide. This is because if you do not do that, then you are not able to close the path at infinity, that is to deform continuously the integration contour from the original one, the orange one, to the gray one, okay? In order to connect the path at infinity with semicircular arcs, then you need to introduce this additional green vertical steepest descent path, which is by definition the lateral wave, since the lateral wave is by definition the steepest descent contribution that is associated with the wave number in the medium where the source is not present. So in this case, the wave number of the upper half space, whereas the source is in the lower half space, okay? Let's see what's the role of this lateral wave. The analytical expression, to have it in front of us, is the following. It's an integral along the steepest descent path number 1 of the usual integrand that we already described before. Now, along the steepest descent path number 1, which is vertical, we may let k rho, the integration variable, equal to the wave number k1 minus js, where s is a positive real number. That's because we are going all the way down vertically from k1 down to minus imaginary infinity. So we can integrate with respect to this new variable s. However, we need to take into account that the integration path is folded. So as you can see, there is an upper part, which is here indicated with a solid green line, which runs in the top Riemann sheet. That is the Riemann sheet where all wave numbers have a negative imaginary part. And instead, there is a lower part of the steepest descent path, the one represented with a dashed green line, that instead crosses the branch cuts. Okay, so both wave numbers are improper in the upward leg. Let me say more precisely that the downward leg, the one represented here with a solid green line, is not on the top Riemann sheet. That was wrong, since it crosses a single branch cut, the one here represented in light red. So with respect to the KZ2 vertical wave number, we are improper, whereas with respect to KZ1 wave number, we are proper. And this is what we have at the bottom of this slide. So the downward leg of the steepest descent path is indicated with a plus here. That must be evaluated with the proper determination of KZ1, that is the determination with the negative imaginary part, whereas KZ2 has a positive imaginary part, so it is improper, and it does not satisfy the radiation condition at infinity. Whereas on the upward leg of the steepest descent path, indicated with a minus, we have both vertical wave numbers improper, so the imaginary part for both is positive. Okay, let us see in detail this folded reflection coefficient, that is the difference between the plus and minus determinations. The reflection coefficient minus gamma Tm has this expression here, and this is a ratio of linear combination of wave numbers by multiplying both the numerator and the denominator by the denominator with the minus sign. What we get is that we have in the numerator now a square of the binomial that was originally present, whereas in the denominator we have a difference of two squares. So by performing some algebra, we can split this fraction into the sum of two fractions that are here indicated with the black and green colors. There is a fundamental difference in those two contributions, because the fraction in black involves only squares of wave numbers. So now it's not important if we are on one Riemann sheet or another, because when you square, you lose any information about the determination of the square root that defines the wave numbers. And so this part in black is not a multi-valued function. This is a single-valued function with no branch points. So if you calculate it on the downward leg or on the upward leg of the steepest descent path, then it has the same values on the two parts. And when you subtract those two values, you get 0. So this black part does not give you a contribution to the folded reflection coefficient, which is the difference of the plus and minus determinations. What does contribute is the green part, because in this part you can see in the numerator there are the two wave numbers without the square sign. Okay, and in particular, since we have that the two legs of the steepest descent path differ because of the determination of the KZ1 wave number, which is proper on the downward leg and improper on the upward leg, then the difference between the two determinations comes from KZ1. So basically, we need to evaluate this folded value of KZ1. So now we can focus on this wave number KZ1, which is the square root of K1 squared minus K rho squared. And since we are on the vertical steepest descent path, we can let K rho be equal to K1 minus JS. So in the end, KZ1 is equal to the square root of 2JS plus S squared. Let me see if everything is okay. Okay. On the other hand, KZ2, with the same steps, can be represented as the square root of k2 squared minus k1 squared plus 2js plus s squared. So as you can see, when you let s tend to 0, kz1 tends to 0, whereas kz2 tends to a non-zero number, which is the square root of these two terms here. Why we should let s tend to 0? Well, because we wish to use Watson's lemma to evaluate asymptotically the steepest descent path integral. And Watson's lemma tells us that in order to determine the asymptotic behavior of the integral, we need to determine the local behavior of the integrand in the neighborhood of the branch point, which is k1, that is when s tends to 0. In this limit, the square root that defines kz1 tends to the square root of 2jk1s, because we can neglect s squared. And so we see that kz1 goes as a constant times s to 1/2. And there is also a further factor, which is -1 minus j, if we select the proper determination, and 1 plus j if we select the improper determination. And as you can see, the proper determination has a negative imaginary part, whereas the improper has a positive imaginary part. On the other hand, kz2 tends to a constant in which s is not present anymore. So in the end, the folded value of the reflection coefficient minus gamma Tm has the expression that is reported here. And now we are in a position of evaluating asymptotically the lateral wave by letting gamma 0 be this bunch of numerical constants. We have that the folded reflection coefficient minus gamma is given by gamma 0 times s to 1/2. If you insert these inside your integral and you take outside the integral all the other constants that do not depend on the integration variable s, what you get is the usual gamma function with argument 3/2. If you change variables, you will see that a term like rho to 3/2 appears in the denominator, which joins the term rho inside this square root, in the denominator inside this square root, to build up the overall behavior of the lateral wave, which is 1 over the second power of rho. So the lateral wave has this expression in the box that we will now comment, in which, in addition to a numerical constant, there is an exponential, a phase exponential. As you can see, the exponent is purely imaginary. And then there is an amplitude coefficient, which goes like the inverse of the square of the radial distance. Okay. Let us see what is the meaning of this lateral wave that we have now evaluated asymptotically, and so we can have it in front of us in analytical form. Let us start with the phase. The phase in the exponential is rewritten here, and it can be manipulated a little bit. First of all, we can multiply and divide by this square root here, okay, to get this second black expression, which can be further rewritten in terms of the sum of the red and blue parts. You can check that everything remains the same, and we can express everything now in terms of the critical angle, because the critical angle is such that k1 is equal to k2 times the sine of the critical angle. So, for example, this ratio here in red, k1 divided by the square root of k2 squared minus k1 squared, that is equal to the tangent of the critical angle. Whereas the ratio of k2 and the same square root function gives us the inverse of the cosine of the critical angle, okay? So the second of the critical angle. If we introduce those expressions in the upper expression of the phase, what we get is that the phase of the lateral wave can be cast in the form that you can see here, as the sum of a number of terms. The term in red can be associated with a distance, L2, that you can see represented in the picture here, whereas the term in blue can be written as the sum of two distances, L1 and L3. Now, these three distances, L1, L2, and L3, can easily be seen with a little bit of trigonometry to be associated with the path that originates from the source, goes to the interface, forming the critical angle with respect to the normal. Then it runs along the interface for a while, for a length equal to L2. And finally, we have L3, that is the distance between this red arrow, okay, and the observation point. And again, this blue path, L3, forms the critical angle with respect to the vertical direction. So what we have discovered now is that the phase of the lateral wave that has been evaluated asymptotically correspond exactly to the phase associated with these three paths. And so this gives us a clue that the physical mechanism associated with the lateral wave is exactly the one that we had introduced in the initial slides. Let me come back. Okay. Here we had imagined a mechanism in which there was a critical impinging ray that goes along the interface for a while and then comes back in the lower medium. This is exactly what the phase of the lateral wave evaluated asymptotically has told us here. Okay, so the lateral wave in practice does exactly this. Okay, it's a path that is followed by the electromagnetic radiation, and note that in part of this path, the wave is evanescent transversely, because when we run along the interface, we have an evanescent behavior of the wave in the upper medium, as is typical of the refracted wave associated with the critical angle, okay? Now, it is also interesting, remaining with the phase, to observe that the lateral wave does not exist everywhere. There is a domain of existence if the source is very close to the interface, and in this picture I have put the source exactly at the origin of the reference system. Then the domain of existence of the lateral wave is defined by this oblique line here, which forms the critical angle with respect to the vertical direction. Now, inside the domain of existence, the lateral wave propagates as a uniform plane wave with a wave number K2, which is the wave number of the lower medium. So here you can see the wave fronts that are straight inside the domain of existence. Those straight wave fronts connect the circular wave fronts that exist in the lower medium here in this wedge, where you have instead a spherical wave that propagates inside the lower medium, and that comes from the saddle point contribution, as we saw in the previous lesson. That's the dominant asymptotics in the lower medium. As well, it connects with the spherical or circular, in this drawing, wavefronts that exist in the upper medium, where for the same reason we have a saddle point contribution that is in the form of a spherical wave, now with the wave number K1, okay? The matching comes directly from the fact that beta rho along the interface is equal to K1, and that's equal, by definition of critical angle, to K2 times the sine of the critical angle. So everywhere there is phase matching. There are no discontinuities in the wavefronts that are matched along the places where the boundaries of the domain of existence of the lateral wave, and those are called technically the shadow boundaries of the lateral wave, because outside those boundaries the lateral wave does not exist. So they are shadow regions for the lateral wave. It's also interesting to observe the behavior of the lateral wave as concerns the amplitude. As we saw, the order of decay of the lateral wave is 1 over rho squared. Now, this is larger than that of a spherical wave, which goes instead like the inverse distance, 1 over rho. Hence, the lateral wave can be described as a diffraction effect that is weak than the direct and reflected geometrical optics fields that are associated with spherical waves. When you have an observation point at the interface, the direct and reflected geometrical optic terms tend to cancel each other, especially for large radial distances. And this is the case in which the steepest descent path associated with K2, so the wave number in the lower medium, is vertical. And in this case, it gives rise to a wave that decays slower than 1 over rho. So it's, sorry, faster than 1 over rho. So it's 1 over rho to 3 over 2. However, this is still slower than 1 over rho squared. So this contribution is still dominant with respect to the lateral wave. There may be exceptions in which you can observe easily the lateral wave, and that occurs, for example, in non-uniform media. In the bottom of this slide, you can see an example. You have a source here on the z-axis that launches rays in a non-uniform medium whose permittivity profile along z is represented on the left. Okay, so the permittivity profile is such that the rays, which describe curves, and they are not straight because the medium is not uniform, they form a caustic. So you can see there is this dashed line, the caustic, and on each point on this dashed line, there is a ray which goes tangent to the caustic, as we described last week. And so there occurs a shadow region which cannot be reached directly by any of the rays that originate from the source. So the geometrical optics dominant asymptotic term, which is associated with rays emanating from the source, they do not reach this shadow region. However, this shadow region can be reached by the lateral wave, because you may consider, for example, this ray here with this thicker line that impinges upon the interface at the critical angle. Then it travels along the interface and goes into the shadow region, refracting back in the upper medium, like the lateral wave does. So in this case, the lateral wave becomes the dominant asymptotic contribution because there is no geometrical optics contribution that overcomes it in this shadow region. Okay, so this is a very special situation, one of the few in which you can observe directly the lateral wave in the frequency domain. Very different is the situation in the time domain. In the time domain, it's easy to detect the lateral wave because in the transient condition, each wave species has its own speed, so it arrives at the observation point at different times. So you can distinguish the various wave species by observing things at different times. So, for example, if you consider the direct and reflected wave fronts originating from the source, which is placed close to the interface between the two media, then that's a spherical wavefront that propagates with a certain phase velocity, c1, for example. So here you see the radius of this half sphere is equal to c1 t, where t is time now. However, we also have a lateral wavefronts that propagate with straight lines in this drawing, which is a two-dimensional cross-section. So you can imagine that the actual wavefront of the lateral wave is conical because you should rotate those straight segments around the vertical z-axis. So we have this conical wavefront that also propagates with velocity c1 inside the same medium. Then in the upper medium, we have a spherical wavefront that propagates with velocity c2, which is larger than c1, because the medium in the upper half space is less dense optically. When you put everything together, you have a composite wavefront, and there are regions, those indicated with yellow arrows, in which the lateral wave is the wave that arrives first to the observer. So before the directed wave, arrives the lateral wave, which for this reason is also known as the head wave, because it's in the head of the transient waveform that is observed at the observation point if this is located in one of those regions. Okay? And we will say something more about lateral waves in the time domain next week when we will deal with transient. Okay? Okay, now I think it's time for making a 10 minutes break, and then we will go into surface and leaky waves. So, see you in 10 minutes. Okay, I think we can start again. Can you hear me?
Yes.
Okay, thanks.
Yes.
Okay, now let us say something about surface and leaky waves. Consider now a generalized multi-layer structure, like the one which is represented here, in which you can see there is an upper medium, half infinite, semi-infinite with wave number k1. Then there is a slab with wave number k2 and another slab with wave number k3. And then finally another semi-infinite medium with wave number kn. Now, by definition, surface waves are those wave constituents that rise in a spectral representation of the field as residue contributions of poles located on the proper sheet. So the situation in the complex plane is the one that you can see reported here. There are the two pairs of branch points, k1 and minus k1, associated with the wave number in the upper semi-infinite medium. And then there is another pair of branch points, kn and minus kn, associated with a medium in the lower semi-infinite medium. All the remaining wave numbers in the intermediate layers having finite thicknesses, they do not produce multi-valued square roots inside the integrand, and therefore they do not introduce additional branch points. So the rule is, every time you have a semi-infinite medium, then there is a pair of branch points associated with that medium. In this case, so we have two pairs of branch points and the associated branch cuts that, as usual, are indicated with those wiggly lines, and we choose the Sommerfeld branch cuts that are hyperbolic, and when the wave numbers are real, they go through the real and imaginary axis. It is possible that inside on the top sheet, on the top Riemann sheet of the four sheeted Riemann surface, there are poles, and in this picture you can see a pole on the real axis, k rho surface wave plus its negative counterpart by symmetry on the negative real axis. And by definition, the poles located on the top Riemann sheet, those are associated with surface waves. One example is the Zenek wave that we already encountered. In that case, since the dielectric medium in the lower half space was lossy, the wave number was complex, so the pole would not occur on the real axis, but instead in the fourth and second quadrants of the complex plane. However, in the absence of losses, like in a multi-layered lossless structure, then the pole would be located on the real axis, and therefore the surface wave number, k rho surface wave, would be a real number. So no attenuation in the exponential that describes the propagation of the surface wave. For a real surface wave pole in particular, what happens is that the wave attenuates exponentially at infinity in the transverse direction, so along the z direction, both in the upper and in the lower semi-infinite media. That's more or less the structure of the Zenek or surface plasmon polariton waves that we already discussed in our previous lesson. Instead, if you observe what happens in the transverse plane, in the xy plane, then in this plane the wave is described by a Hankel function of the second kind, which asymptotically behaves like an exponential e to minus j k rho surface wave times rho, divided by rho to 1/2. This is the typical behavior of a cylindrical wave. The spreading factor in the denominator is typical of two-dimensional propagation, and it must be this spreading because of power conservation, of course. The exponential gives us the phase variation along the radial direction. And of course, inside the intermediate layers, you will have, instead of exponentials, you will have trigonometric functions along z, describing the transverse profile of this surface wave. If there is a ground, and that is a very common situation at microwaves, consider, for example, microstrip structures, or more generally, multi-layered microwave integrated circuits, then for those structures, you have a metal ground plane that completely shields the electromagnetic field, which is not allowed to go in the lower half space. So there is no wave number associated with the lower half space because there is no field in it. And so in this case, you only have one pair of branch points, those associated with the wave number k1 in the upper semi-infinite medium. So the situation is somewhat simpler. You have here the integral along this branch cut, which give you the continuous spectrum of modes. And then there is the residue contribution in this pole, from this pole, that gives you the discrete spectrum. Okay, typically at a given frequency, only a finite number of poles exist on the top Riemann sheet, which means that the discrete spectrum is constituted by a finite number of cylindrical waves. Okay, if the structure were completely closed, for example, a parallel plate waveguide, so you also have a ground plane on top of this slab in pink, then in this case you don't have any semi-infinite media, so you simply don't have branch points. So you remove from this picture the branch points and the associated branch cuts, and what you are left with is a single Riemann sheet, so a single complex plane with poles. A finite number of those poles will be located on the real axis, and those are the modes above cutoff of the parallel plate waveguide. And an infinite number of poles are located on the imaginary axis, both positive and negative, and those are the infinite modes below cutoff of the parallel plate waveguide. As you change frequency, for example, when you increase frequency, more and more modes will go in propagation, so frequency will become higher than their cutoff frequency, and you can imagine this infinite number of poles on the imaginary axis that progressively move and go to the real axis when they go above their cutoff frequency. Okay? This is what would happen in a completely closed planar waveguide. But since here we are dealing with open planar waveguides, we need to introduce branch points and the associated branch cuts, and the structure is more complicated because you don't have a single complex plane, but you have a Riemann surface that in this example is constituted by two complex planes, the top one where everything is proper and satisfies the radiation condition at infinity, and the bottom Riemann sheet where everything is improper and does not satisfy the radiation condition at infinity. The latter...
Can I make a question?
Sure.
Because I did not get exactly the difference between a closed waveguide and open waveguide.
An open one. Sure. Well, from a physical point of view, the closed waveguide is one in which you have two ground planes, two metal plates, one at the bottom of the structure, as in this picture, and another one which is not in this picture, but you can imagine to be placed on top of this pink layer, okay? So the electromagnetic field is confined in the space bounded by those two metal plates.
Okay.
And it's not present outside. So that's a closed waveguide. Propagation occurs only in the radial direction, but there is no electromagnetic field going to infinity in the vertical direction, okay? Now, since the vertical wave numbers, kz1, kz2, etc., are defined by square roots, okay, it is possible that those square roots introduce branch points. For the intermediate layers, having finite thickness, however, those square roots do not introduce branch points because, for example, you would find them as the argument of functions that are even, like the cosine, the trigonometric cosine function. So it does not matter what determination of the square root you choose, because once you are inside the argument of a cosine function, which is even, either if you choose one determination or another, then everything remains the same, because the cosine function remains the same if you change the sign of its argument. So this is what occurs for the layers number 2 and number 3, whereas for layer number 1, if this layer is semi-infinite, that is, the structure is like the one in this figure, then the square root that defines the vertical wave number, that defines a two-valued function. So for this reason, you need to introduce the two branch points, K1, and the associated branch cuts that are chosen as the Sommerfeld branch cuts as in this figure, okay? So whenever you see branch points and branch cuts, you know that you are talking about an open structure, because a closed structure would not have those. And for a closed structure, everything is simpler. You must only distinguish between propagating modes or modes below cutoff. However, you only have a discrete spectrum. Instead, for an open waveguide, in addition to a discrete spectrum that arises from poles, you also have a continuous spectrum that arises from the integration along this green path that runs along the branch cut, okay, the Sommerfeld branch cut. So this is typical of open structures. In addition to discrete modes of propagation, the surface waves, you also have a continuous spectrum of modes which are useful to describe radiative phenomena and also reactive phenomena. This is the description of what happens in an open waveguide if you stick to the spectral representation, that is the deformation of the integration path from the original real axis to what you see in this picture. Okay, so green path plus blue path. However, it is possible to use a non-spectral deformation in which you go through the steepest descent path that runs through the saddle point located at K1 sine theta, where theta is the observation angle. Now, this steepest descent path does not remain entirely on the top Riemann sheet where the radiation condition is satisfied, because it crosses this wiggly line, the branch cut, and it goes down to the bottom Riemann sheet. So if you deform your integration path from the original real axis to this gray path here, the steepest descent path, what happens is that you may sweep across poles that are now located on the bottom Riemann sheet. And one example is this pole here, which is encircled by this dashed orange circle. Okay, by definition, leaky waves or leaky modes are those residue contribution that come from poles located on the improper Riemann sheets. Okay, at least this is what happens in the most common situation in which leaky poles are only improper. It is also possible that leaky poles are proper, but we will not discuss this in this course. So as far as simple structures like the microstrip structures are concerned, improper poles, those on top sheet, are surface waves. Improper poles are leaky waves. Okay. Note that since we are in the improper Riemann sheet, the imaginary part of the vertical wave number of the leaky wave is now positive, which means that the wave is not exponentially attenuated at infinity in the vertical direction, but rather it exponentially increases at infinity in the vertical direction. Something which is very peculiar of leaky waves and which constituted a big problem for the first who studied this kind of waves in the 40s and 50s of the last century. That's because, of course, you cannot have a physical wave that exponentially increases to infinity. But we will see how to solve this problem in a moment. Let us say explicitly then that the wave number of a leaky wave is always complex, with a phase constant beta and an attenuation constant or leakage constant alpha, which is present also if all the media are lossless. So this imaginary part is not only associated with material losses, because these could also be absent. However, there is in any case an imaginary part in the wave number of a leaky wave, because this is associated with power leakage via radiation. So we have an attenuation of the leaky wave because the leaky wave loses its power progressively during its propagation, and it does so because it radiates. Hence the name leaky or radiation mode that we give to this kind of wave, from the verb to leak, which means to lose something progressively, like a tap that leaks water. In this case, we have an open waveguide whose mode leaks power during its propagation. This is true at least if the imaginary part is not too large. Otherwise, if the imaginary part is too large, in particular when it is larger than the phase constant, then radiative effects are more or less negligible and reactive effects prevail. And in this case, the leaky mode behaves much as an ordinary mode of a closed waveguide, which is below cutoff. So it's evanescent. Let us see more in detail when the leaky mode comes into play. Consider that you have an observational angle that changes, and in particular it increases when theta is smaller than a certain threshold value, theta threshold. You have this gray path here, which goes in part down in the bottom Riemann sheet, and this is the dashed part there. Then in this case, you do not intercept the pole which is located on the bottom Riemann sheet. Then there is a critical angle, a threshold angle, better, by which the steepest descent path, now in purple, goes exactly through the pole, the leaky pole. If you increase further the observation angle, then you sweep across the pole and you capture it, so you should introduce the residue contribution in the representation of the field. Now it's easy to see that this threshold angle is such that the saddle point, which is K1 sine the threshold angle, is larger than beta, which is the real part of the wave number of the leaky pole. As you can see easily in this figure, the saddle point is on the right of the pole when you are on the threshold angle. Now, if the attenuation constant is small, however, which is not the case in this picture, you should imagine that the pole is now very close to the real axis. If this occurs, then the pole and the threshold saddle point will be very close one to each other, and therefore you may let K1 sine theta threshold more or less equal to beta. Okay, this is a good approximation if alpha is negligible with respect to beta. So to resume, when the observation angle is larger than the threshold value, the leaky pole is captured, and so it contributes to the representation of the field in a steepest descent path representation. Otherwise, it is not captured and it does not contribute to the field. In practice, this means that when the angle theta is larger than this threshold value that defines this conical region with the z-axis as its rotational axis, then when theta is larger, I was saying, we are inside this shaded region where the leaky mode exists. And inside this region, you can see the improper behavior of the wave, which grows exponentially along the positive z direction. However, this exponential growth stops at the critical angle, the threshold angle, outside which the leaky mode does not contribute to the field. So it does not go all the way to infinity in the upper direction, because at a certain point, at this wedge, it must stop. So we have a cylindrical wave that propagates, and it increases exponentially inside the region where it exists. Why this exponential increase? Well, you can imagine, we will see that in a moment. inside the region where the leaky wave exists, the leaky wave is represented by a plane wave. However, this plane wave is not uniform because, as you can see, there is a phase vector beta and an attenuation vector alpha. The phase vector forms an angle with respect to the vertical axis, which is somewhat smaller than the threshold value. If alpha is a small quantity, this angle is very close to the threshold value. However, the two angles are not exactly the same. So you can see in this figure, I have exaggerated the fact that beta, the vector beta, is not parallel to the threshold line at the angle theta threshold, okay? It is easy to prove, and that's an exercise for you, that also for leaky waves, there is phase matching at the interface, which is the shadow boundary of the leaky wave. There is inside the region of existence of the leaky wave, you have rectilinear wavefronts in this cross-section, and so conical wavefronts if you rotate everything around the z-axis. Whereas inside the upper region, you don't have the leaky wave, you only have the geometrical optics contribution, which is a spherical wave. So in this picture, you can see circular wavefronts. And those wavefronts match at the shadow boundary, okay? So there is no phase discontinuity. Here is the reason why you should have the exponential growth at infinity of a leaky wave. That's associated with the fact that while the leaky wave propagates in the radial direction, rho, then it loses power by radiation. So this power goes as an exponential function of rho, e to minus 2 alpha rho. This 2 factor comes from the fact that the power is quadratic in the field. So if the field decays with alpha, the power decays with 2 alpha. Now consider the rays that emanate from the upper interface and go in the upper medium because of radiation. Then the ray that emanates from this point here close to the source contains some power, but the ray that comes next will contain less power because something has been radiated before, and so on. So if you consider rays that exit the structure for larger and larger values of the radial distance, rho, then the power associated with each of those rays is decaying because of the exponential decay of the leaky wave in the radial direction. However, if you now observe things not as a function of rho, but as a function of z, at a fixed value of the radial distance, so you observe things along this dashed line, what you see is that you run into progressively different rays, and if you increase z, you start with rays that carry small power, then you encounter progressively increasing power associated to the rays, exactly for the same reason that I have described before. So with this simple ray optical representation of leakage, you can understand why you should find an exponential increase of the field that is associated with the exponential decrease of the field in the radial direction. Of course, this occurs until you reach the shadow boundary, which is defined by the threshold angle, after which the leaky wave does not exist anymore. And so in that case, you go into the region where you have only the geometrical optics contribution. Why leaky waves are important in practice? Well, since a leaky wave is exponentially attenuated in the radial direction within its angular region of validity, it does not contribute directly to the far field because it's negligible with respect to any algebraic decay like the decay of a spherical wave, which is 1 over rho. However, if those 3 conditions stated here are satisfied, that is, the leaky pole is captured for some angles, and for being captured, its phase constant must be less than k1, so it must be radially fast, because its phase velocity must be larger than the velocity in medium 1. And in addition, if it is close to the real axis, so alpha is much less than beta, which means that the leaky wave is only weakly attenuated. And finally, if its residue is not negligible, so the source couples power into the leaky wave, so the residue in the leaky wave pole is not negligible, and this means that physically the leaky wave is well excited by the source, then the leaky wave pole may well provide the dominant contribution to the integrand in the part of the integration domain between the origin of the k-row plane and the wave number k1. Since this portion of the integration domain is what we call usually the visible region, so this contributes directly to the shape of the far-field pattern, then it is possible that the presence of a single leaky wave pole may substantially determine the shape of the far-field pattern of your antenna. And this is the principle that is underlying the behavior of an entire class of radiators, which are known as leaky wave antennas. Since the far-field pattern is proportional to the Fourier transform of the aperture field, and since the aperture field may be dominated by the excitation of a leaky wave, then again we come to the conclusion that the pattern may be essentially established by the excitation of a leaky wave along the structure. Here you can see in the bottom part on the left an example of a one-dimensional leaky wave antenna, which is a slotted rectangular waveguide, which is historically the first example of a leaky wave antenna. This was proposed more or less during the Second World War. And here you can see the rectangular waveguide, which is a closed waveguide and therefore would not radiate, is made open by introducing progressively a slot. In the slotted portion of the waveguide, the spectrum becomes different, the modal spectrum. In particular, we may see that there are leaky modes, and it is possible that with those leaky modes, you shape the pattern of your antenna. And this is a very versatile way of shaping the pattern. It is also possible to have two-dimensional leaky waves, as in the example we discussed today of a vertical dipole in a planar structure in which the wave propagates as a cylindrical wave. And in this case, the pattern would be conical, with an angle of radiation which is mainly determined by the leaky wave, and also a beam width, delta theta, which is also mainly determined by the leaky wave number. Here in this final slide, you can see more exactly what happens. Here you see a pictorial representation of the absolute value of the pattern function as a function of the complex angle phi, which has a real part, phi r, and an imaginary part, phi j. This generalizes the usual real angle theta, which is the argument of the pattern function of this antenna. If you examine what happens on the real axis, what you see is this red curve, which gives you the shape of the radiation pattern as a function of theta, which is phi r, that goes from 0 to pi over 2. Now, this pattern has a very peaked shape. You can see there is a sharp maximum. Why is that? Well, the reason is that near the real axis, there is a leaky wave pole. You can see this with this color bar. Black means small absolute value, whereas white means high absolute value. So where you see light colors, you can imagine that the function of this complex variable phi has a big absolute value. So when you are in the vicinity of a pole, of course, the absolute value of an analytic function goes to infinity. So you can see that the existence of a leaky pole in the complex plane in the vicinity of the real axis determines basically the appearance of this spike. So a main beam in the radiation pattern whose location is mainly established by the real part of this pole, okay? So the leaky wave phase constant beta, whereas the amplitude, the width, sorry, of the pattern, of the peak, of the main beam, is established by how far the pole is from the real axis, so the imaginary part of the pole, that is the leaky wave attenuation constant. In addition to a leaky pole, in this example, you can see also a surface wave pole, which is located, however, far from the visible region, that is far from the real axis, because it's located on the exactly where the real part of the angle phi is equal to pi over 2, and the imaginary part is instead different from 0. So here we have an evanescent wave, which is transversely evanescent, and that's a surface wave which does not contribute directly to the radiation pattern. As we know, surface waves by themselves do not radiate, whereas leaky waves directly radiate because they may be very close to the visible region of the spectrum. Surface waves in an infinite structure do not radiate. The only way to let a surface wave radiate is to introduce some discontinuity. So a surface wave may be let radiate if you truncate the structure. So, for example, you truncate the substrate that supports the propagation of the surface wave. At the truncation, diffraction effects occur, and these diffraction effects translate into radiation in free space. That's the principle of another class of antennas that are called surface wave antennas, that are, however, less versatile than leaky wave antennas, because with surface wave antennas, you cannot control the direction of propagation, because propagation occurs only in the end-fire direction, that is, in the direction where the surface wave propagates. Whereas the leaky wave pole is characterized by the dispersive nature of any mode in any waveguide, that is, its phase constant varies with frequency. So if you vary frequency, then the location of this pole in the complex plane moves, and this in turn means that the peak in the radiation pattern will also move. So what you have is a scanning of the beam, an angular scanning of the beam in the far field by varying frequency, which is something that may be desirable depending on the application or not. For example, if you have a radar, that may be useful to scan angularly the region of interest. Okay. I have to thank my colleague Walter Fuscaldo for this beautiful picture that he has prepared for us. Okay, I think I have said everything for today. The content of this last lesson can be retrieved more or less in these sources. In particular, as concerns lateral waves, there is a very complete research report by Leopold Felsen, who was a giant in the field of wave phenomena. And there is also, of course, the book by Felsen and Markowitz, Radiation and Scattering of Waves, that contains everything. So it contains also lateral waves and leaky waves. In particular, as concerns leaky waves and leaky wave antennas, the best references are those by Hessel and Zucker, and in the classical book edited by Collin and Zucker, Antenna Theory of 1969. It's an old book, but it's still one of the best references, in particular on the class of traveling wave antennas, which contains, as particular cases, the leaky wave antennas and the surface wave antennas. Okay, I think I will stop here. For this week, it's everything. So next week, we will address transient phenomena, and that will be the final week of this course. Thank you very much for your attention.
Can I have?
So please.
Thank you.
Can I ask
Sure.
just a
Sure.
sorry, a curiosity, because I don't know much about radar. So, but why you are interested in the liquid waves? Why are you interested for a certain wave profile, as such the one you showed before?
Well, in general,
because you told that it's interesting for other applications.
No, there are also other applications because it is also possible to have leaky waves that do not scan with frequency. So you have a fixed beam by varying frequency. So actually, leaky waves are used in a bunch of applications. The main point with leaky waves is that exciting a leaky wave is simple. You just need a simple source. And the shape of the radiation pattern is then determined by the leaky wave number. So if you are able to control that wave number, and that depends on the cross-section of your waveguide, because as in any guided wave problem, the modal spectrum, that is the value of the wave number of the modes, is defined by the shape and the media that are involved in the cross-section. So if you are able to control the wave number of the leaky mode, then this translates into your ability to control the shape of the radiation pattern. Typically, you wish to have directivity in your radiation pattern, and that can be easily obtained with leaky waves if you have a leaky wave that is weakly attenuated, that is small alpha, because in that case, the leaky pole will be very close to the real axis, and as you can imagine, this spike grows and becomes steeper and steeper and sharper. So in the limit, it would become a delta function if the pole could reside exactly on the real axis. So in this way, you can have very directive beams. But there is even more. If you change the shape of your cross-section progressively, as in this example here on the left, so you change the cross-section of your waveguide along the direction of propagation of the mode, as in this case, in which you have a slot whose width changes during the propagation of the mode. Okay, so for each cross-section, you have a different wave number of the leaky wave. And if you manage to maintain the phase constant beta almost the same, and instead having the attenuation constant vary along the structure, then it is possible for you to control the aperture field, and so to obtain by Fourier transform radiation patterns with some desired shape. So you can make the synthesis of the pattern. So you may enforce, for example, to have a cosecant pattern, which is useful in radar, or whatever pattern you wish, by simply controlling the illumination aperture. And that can be quite done in a quite versatile way using leaky waves. Okay, so leaky waves are also an effective tool for synthesizing the far field pattern. Exactly. I hope I have answered to your question.
Yeah, more or less. I guess that the leaky waves are quite easy to manipulate.
Exactly.
That's the philosophy behind it.
That's the point. I have to add, since I know that you deal with optics and also guided waves in optics, that leaky waves are not always seen as something useful. That's the point of view of an antenna designer, as I am, but they are sometimes seen as a problem, because many times you wish to propagate a signal along an open waveguide, like an optical fiber, and you do not wish radiation to occur. However, as you may know, in optical fibers, there exist leaky modes, and in that case, they are undesired. They are associated with the so-called leaky rays of the waveguide, and you should avoid exciting them. So it depends on the application. If you are a guided wave man, then you should avoid leaky waves.
No, indeed, that motivates a bit my question.
Yes,
actually.
I could imagine. Okay. There was anyone else?
Okay, thank you.
You're welcome. Okay, no further questions? Okay, so thank you again for your attention. As usual, I will post the slides in the course website, and in a few minutes also the recording will be available in the usual Google Drive shared folder. Okay. So thank you again, and see you on next Tuesday, when hopefully I will be able to do our lesson in presence. Otherwise, I will let you know.
I will be at distance
Anyway.
on Tuesday, I guess.
Oh.
I guess yes, because unfortunately I have my flightmate with fever, so I have to be isolated as well.
Yes, I understand, and it's not unlikely that some of us, including myself, will have the same problem, because I had two sons that were isolated because they had classmates who were positive. So last week we had to do everything more or less at a distance. But anyway, let's hope well. Okay. Let me know also, Simona, if you will not be there, because in that case I will do the lesson at the distance only. Okay. Okay, thank you. Yes. Bye-bye.
Bye.